Okay, so to move on to the next set of lecture materials for week 4, we're going to be looking at the process of quantization. So our learning aims in this series of slides, we want to understand the role which is played by quantization in communication networks. So quantization is essentially the next step which is played after the sampling of the signal. So we've got an analog signal, an analog continuous signal that we're sampling, and we want to digitize this signal. We want to assign a discrete range of values to this continuous signal, and it's through quantization that this is actually achieved. So we're essentially assigning numbers to the sampled range. We want to become aware of the different ways in which quantization may be achieved. So there's a number of different ways which vary in terms of the amount of levels, for example, the amount of information which is communicated in each quantized level. So they have different levels of efficiencies. The different types include linear, non-linear, and compounding. So we want to think about the different ways in which quantization may be achieved. We want to understand how we can calculate these quantization levels. So how many levels should be used in order to digitize a continuous signal. And we also want to appreciate the existence of quantization noise. So whenever we're assigning a discrete signal to a continuous signal, an originally continuous signal, we will actually end up with an approximation of the values for the discrete signal. And this is also known as noise. So we're reducing some of the accuracy, introducing some error into the digital signal which is being communicated. So quantization deals with the conversion of a continuous signal to a discrete signal which may be transmitted across a communication channel. So our continuous original signal is modelled as a continuous wave. So there's an infinite range of values which may be used to represent our continuous signal. These are also known as our analog signals. So a continuous model is convenient for some situations, such as our audio signals, our sound information, where the values can take on a wide range of values. Also for the communication of human sensor data, which again can take a wide range of values and should be specified in a good level of accuracy to ensure that reliable operation of this data takes place with regards to the human life. So a continuous model, a continuous signal is convenient for some situations, but in other situations it's more convenient to work with digital signals which need to be communicated across the communication channel. So whenever we're working with the digital signals, we're using a discrete range of values. So we're restricting the continuous range of values into a finite range of values, and we communicate the continuous signal using this finite range of values. So quantization is the next step after we sample our continuous signal. So we sample our continuous signal at least twice the maximum frequency of the signal. And the next step in the conversion of the signal in order to be communicated is quantization. So we actually want to assign the values, the discrete values, to these samples which may be communicated. So most devices that we deal with use both analog and digital signals. Digital signals are particularly robust to noise, so we have a finite range of values being communicated, and alongside these values we will encode error detection and correction mechanisms, and these can be used on the receiver side of the network in order to detect and correct any errors which may be introduced during the communication process. But in certain situations, analog signals may be more appropriate or even essential, really. So, as I've mentioned, in the case of human sensors, for example, continuous, that infinite range of values is necessary to communicate the amount of information which may be needed. So this conversion between analog signals and digital signals is a very important part of our communication process systems. So it's important to note that after we sample our signal is not just ready to be sent. It's not yet completely digital because the values can still take on any number from the continuous range. So we need to convert this continuous range of values into a discrete finite range of values. Okay, so in order to be able to represent each number from a continuous range, we would need an infinite number of digits. Okay, so we want to reduce that infinite number of digits to a finite range, and this is the main functionality of the quantization process. So to provide an example as to how quantization may be applied, assume we are communicating a sequence which takes on values in the range between -1 and +1. Assume that we must represent each number from this range with just 2 decimal digits, so one before and one after the decimal point. So our possible values therefore become -1, -0.9, and so on up to 0.9 and 1. Okay, so we have a discrete range of values which we may use to communicate our continuous wave. So using this coding mechanism, there are exactly 21 distinct levels for communicating the amplitude. Okay, so we've got a discrete range of values which we may use to convert, to digitize the continuous signal. So each level is a step of 0.1 higher than its predecessor, and this is the quantization step size. Okay, so we assign each number from our continuous range to the quantization level which is closest to our actual amplitude. Okay, so we're not exactly representing necessarily the actual value which was recorded. We may be introducing some error here by using this approximation. So the range, for example, -0.05 to +0.05 maps to the quantization level 0. Okay, so we're losing some level of accuracy here, but that's just part and parcel of the network communication process. So we're continuously applying this mapping between our discrete values and our continuous signal. Now, as well as introducing some error, there may be some clipping which takes place at both plus -1. Okay, so any values which are larger than 0.95 are mapped to the level 1, no matter how big they get, and the same at the other end, any values larger than -0.95 are mapped to the level -1. Okay, so this is a clipping operation where any values larger are actually clipped and restricted to that size, so allowing us to transmit a discrete range of values to represent our continuous signal. So in general, we can say that information is lost during this quantization process, and discrete valued signals are therefore only an approximation of the continuous value signal. Okay, so information is lost during this process in the communication. So essentially, what is quantization? And it's a process of mapping a large set of input values, a potentially large set of input values, to a smaller set of values. So we're restricting the range of values which may be used to represent a continuous signal. And there's two ways in which quantization may be applied. We may apply rounding and we may apply truncation. Okay, so rounding and truncation are processes which are applied to the conversion of our continuous sampled values in the creation of discrete digital values. So rounding, what does rounding mean? Rounding essentially means dropping digits from a number and adjusting the remaining digits. Okay, so say for example we have a number which is 23.45672. If we round this number, it will become 23.46. So we've both dropped digits from the number and we've adjusted the digits which remain. Okay. In another example, if we have the number 6.39 and we want to round this number, it will become 6.4. So again, we're dropping digits from the number and we're adjusting the digits which remain. So to compare rounding with truncation, we're simply dropping digits from a number. Okay, so for example, if we have the number 12.8392 and we truncate this number, it will become 12.28. So we're just dropping digits from the number and we're not applying any other manipulation of the numbers. Similarly, if we're communicating 23.45672 and we truncate that number, it becomes 23.45. So we're dropping digits from the number and we're not adjusting the remaining digits. Okay, so you should know the difference between rounding and truncation with regards to the quantization process. So quantization replaces each real number with an approximation from a finite set of discrete values. So we're approximating a discrete value for a continuous number from a continuous signal. Issues to consider in the quantization process include how many quantization levels do we need to choose. So how many levels do we need in order to represent the information being communicated? Okay. How should the values of the levels be chosen? And how should we map the values of the original signal to one of the quantization levels? So we'll be looking at those those issues and how we can answer those issues in the remaining slides. But first we want to consider the different types of quantization. So we have the linear quantization, we have the non-linear, we have compounding, and we have our delta modulation. So we're going to step through each of these techniques in the next set of slides.